Okay, so yeah, okay, so yeah, the recording was there's a little bit of a problem with the recording. So what I was saying was that Axiom 54 does not say anything about the post-measurement state, and so we need to look at what are called we need some kind of decomposition of M. So it's sometimes called the Krauss operators or the measurement operators. So instead of P over VM, uh, P over VM M, if you're given the measurement operator, so for each element you also have a decomposition in this form. Then the post-measurement state is given by this object if you see the outcome I. Right? And the probability of seeing this outcome is the same as MI1. Okay, and so this is the section on POVMs, the most general measurement. And when we look at um, quantum channels, so let's do that. Okay, so now section 2.3.2.5, quantum channels and the axioms we stated. Okay. So yeah, we had we looked at the axioms of quantum mechanics, but instead of those, sometimes it's helpful to look at these more general ones. And they're general in the sense that one can show that if you have an environment and a system interacting with each other, then you can and you focus only on the system, then the transformations that you can apply to the system are more general than just unitary transformations, right? And this just characterizes them and gives um, a more convenient mathematical description. So, this- so the axioms, I'm going to be a little bit sloppy with the writing because it's available on the notes. Right. Okay, so the first thing you want is the state, right? So each state is going to be given by a density matrix rho. Um, yes, I'm just going to use okay, Hilbert space and trace rho has to be 1. So that's how we define states. Channels are going to be defined as follows. So, every physical process that acts on a state rho can be represented by a sequence of maps, EI, where EI goes from uh, you know positive operators on H to positive operators on H prime or H sub I, because it can change the dimension of the Hilbert space. And what are the properties to satisfy? So first of all, they have to be so such that this condition is satisfied. Sum over I, EI, acting on rho space is 1. Okay. And the properties that have to be satisfied by each EI is, so each EI satisfies these properties. So the first is that trace of E acting on rho, and this is for all rho and density matrices on A. Okay. So the first one is trace E rho is the probability. Yeah, okay, let's instead of writing EI, let's just say E belonging to satisfies one, the trace E rho is the probability that process E occurred. Right? Yeah, okay. So E is one of these EIs. Okay. Um, so that means in particular that, sorry, this E row has to be between 0 and 1. Okay. Or all row, right? Second is that E is a convex linear map. So E is a convex linear map. What that means is that for any probabilities pi, which I'm acting on some convex combination of rows, is the same as pi acting on R. Okay. And the third is that E is a CPTP map. So what that means is that you can take any Hilbert space identity, and so you can extend E by having identity act on the extended space, and take any A in this on this joint system, joint state. Um, then this thing has to be positive. Okay, so joint state. So yeah. Okay. Um, so that's the last one. And the one about multiple systems is the same as before. Um, Nothing much changed in that set, and that's it. Okay, so for multiple systems, you need to have, zero has to belong to positive H. So this can be a tensor product of at least one, right? Multiple registers. That's fine. And the other thing is that if individual states are unknown to be, say row 1 to row k, then the joint state is row 1 tensor. Okay, where k is the number of systems. Okay. Um, so yeah, so the story is that these axioms are equivalent. So axiom 56, and the initial one, which was 19, equivalent. Here we motivate this fact a little bit. Here we motivate this. For a bit further proof. So we'll not do the full proof. Okay. So how does the theorem work? Sorry. So the way we're going to do it is we're going to look at this very nice characterization of CPTP maps. So E as in axiom 56. Or we can just say that E satisfies these three conditions. Satisfies the three conditions in axiom 56. So this is equivalent to E rho having the following form. It's called the operator sum representation. Right there. Operator sum representation. Okay. And what does it say? It says that the E rho is going to will act as follows. E rho EI beta, and for some EI such that all the ones such that EI dagger EI, the sum is identity, at most identity. Okay. So that's the statement. Now we're going to quickly check that all the operations that we've discussed so far can in fact be expressed in this new language. Okay. So let's go through some of them very quickly. So yeah. Okay, so we'll quickly check that all these operations can be expressed, right? So the first one is unitary evolution.